Hello. Today I would like to share my experience with reading the research paper titled Design of an Optical Photon Counting Array Receiver System for Deep Space Communications. This paper is written by many authors who are all experts in their field, especially in communications. And the whole project, the Mars Laser Communication Demonstration Project, was a part of the NASA's MTO mission titled Mars Telecommunication Orbiter. The MTO mission was discontinued due to the requirement for funding for other projects back in 2007. But this project has been wonderfully completed by the teams at MIT's Lincoln Laboratory, Goddard Space Institute, and also JPL. A lot of work has been done to demonstrate a test bed between Mars and Earth in terms of laser optical communication. The particular research paper that I would like to share my experience with is focused on developing and receiving end, which is consisting of multiple receptors, and all of them are configured in arrangement of an array. I'll go through the paper and we'll see some of the challenges, some of the advantages, and some of the future scope of this technology. This paper is a little bit old, but the experimentation and the results derived within it can be reference for future work in optical communication. As we see an increase in the space missions, and especially with the Artemis generation, the Artemis 3 would have the deep space optical communication on board its system. So it is very useful technology, and I feel that advancing more in this field can help us reach very low latency and high speed communications within our solar system. So I will have the reference paper, the research paper for my reference, and I would like to go section by section and explain try to explain what the content is about. We'll see a lot of different keywords being used here, and we'll see how different technologies have been integrated within this project to make it a success. So first of all, we'll start with the need. The need for optical communication is great in this time and era because we need high bandwidth for communicating real-time sensor data. In earlier times, the requirement for communication was not as much, as we are not communicating high bitrate data. But these days, on every mission on board, we need remote control. We have a lot of sensors trying to identify, say, a new hostile environment like a exoplanet, moon, a comet. Recently, we had the Psyche mission which collected the asteroid samples. So even that was a great example. We need constant data which is of very high quality, say some high quality images, the spectrometry results of some samples. So for this we require very high speed and low latency communication system, which is just not possible with radio frequency. Radio frequency can have a very large rate of divergence, in which the incoming rays will diverge a lot as they reach back to the earth. One novel solution is the optical communications. Within that, we will choose the laser based optical communication because they have very low rate of divergence, about 0.2 micrometer, and also decreasing the rate of divergence will improve our the bandwidth required. So a very high speed data can be transported about 10,000 times the same amount of data within the radio frequency signals. So from this you can easily guess why there is a need for optical communications. This paper especially focuses on building a system that can receive such signals. One proposed solution is creating an array of such say receptors, because there are many reasons for doing that. The first one would be the scalability. We can easily detect the we can say low intensity signals, which was not possible in the one large which might be possible in one large receptor, but then we'll have to make the receptor that large. But during the times when the incoming signal is not that not of that high bandwidth, then the receptor would be just sitting there without any use. So scalability improves the amount of it actually gives us the control of the amount of signal we want to receive. Flexibility is defined here in the terms that we can add any n number of receptors and program them to detect multiple channels simultaneously. So there would be we get the flexibility of adding more receptors if we want. And also as I said before, we can change the amount of the intensity of light in falling to gather the information likewise. One other benefit is that the cost reduction. So while we increase the aperture size of a receptor, the increase in this cost of the receptor is directly proportional to the increase in size, but the coverage area is not linearly proportional to the increase in the overall area of that receptor. So as we give more money and more money to build that telescope, it is not easily seen in the coverage area. So we'll have to spend even more money for the same amount of area compared to the multiple receptors. Also, I would like to say that having multiple receptors can give us an advantage of redundancy. So in case one of the receptors fails or does not give the proper output, we'll not have to just change the whole system. We can very easily just replace it with another receptor which will work fine with the others in an array. The next section gives us some information about the efficiency of that system. Optical systems and telecommunication systems in general are generally described to be efficient in terms of photons per bit. Photons per bit is the count of the number of photons required to process a particular signal. And say you want to transmit 5 bits, then how many photons would you require to transmit those 5 bits is the photon per bit count of that system. The lower the number of photons, the higher the data you can send using minimum resources. So the less the photon per bit count, the more efficient your system is. Traditional radio frequency wave systems are about 20 photons per bit, and that would mean that you would require 20 photons to transmit just 1 bit of digital data. The optical communications, the laser-based optical communication systems are 0.5 photons per bit efficient. That would mean that you can transmit 2 bits within one single photon of that particular signal. So as you can see, there is about 40 times more advantage of using the laser or optical communication system than the traditional radio-based systems. Also, I would like to say that we will see further, but the photon counting technique which is described within this paper is very efficient, not only in terms of the photon per bit, but also in terms of the signal loss, how we can prevent signal loss, and also how we can recover the signal which is lost due to attenuation, distortion, etc. Let's go through the second section of the paper, which is focusing on the photon counting techniques, how that works. So as we discussed, the photon per bit is a very important matter in terms of efficiency of the system. But the efficiency of the system is also a very important thing when we are choosing, especially when we are choosing for space missions. And within that, the ones that are going to go at far distances and would not have a reliable power source. Sometimes the spacecraft may be covered by the shadow of a planet, or maybe orbiting a planet in which it might have like a month of sun-free environment in which its solar panel may not charge. Or it might be a lander which is landing on a planet and may not be facing the sun for say about half a year. That might be possible. So for such cases, we can not have So we cannot have a communication system which takes about half of the fuel to just communicate whatever the data is to be sent. So efficiency also matters in terms of fuel. The more the efficiency, the less fuel or the power required to run it. So I think that for deep space missions, optical communication is the best method. Within that, we will have to choose the modulation techniques of the signal to further increase the efficiency of that particular communication. Many methods are available like frequency shift keying, frequency modulation, phase modulation, QPSK, which is quaternary phase shift keying. But the one selected here is the photon position modulation. Now, what does position modulation mean? PPM is the technique of timing a particular incoming photon, and within that particular photon, which we call a data frame, there are multiple subsections which are divided in terms of time. So say for first 10 microsecond this, then 5 microseconds some other thing, like that. For this particular system, we have divided the data frame into 6 sections. Now those are the first acquisition, which will be like a key to a lock, which will tell us the signal that is incoming is ours and has so and so information within it. Then we have the positioning data frame, which will tell us about the clock or the particular. The next bit is the bit used to tell us more about the size of a particular small section of a data frame, and it will help us dissociate the whole data frame into smaller pieces. The next bit, which repeats every 32 bits, is the synchronization bit. This is completely empty except its middle slot, which is kept at high. Now this creates an impulse signal, which will and the in the receiver will compare two such synchronization bits and synchronize its local clock to the clock rate of the signal. This way we have eliminated the possibility of the clock timings being mismatched, so we can actively change the clock rate to match the same speed with the incoming signal. Now there is the data bit between every two synchronization bit, and after the first synchronization bit there would be a data frame within which we can share whatever information that we may like. So that was the particular data frame within a pulse position modulation signal. PPM has been chosen because it gives very good results in terms of there is a very less distortion. The attenuation rates are also low, and there are various techniques to overcome the different diminishing factors like the environmental disturbances, the solar radiation from which is reflected from the Mars back to the Earth, things like that. To detect this particular PPM, MIT's Lincoln Laboratory has created their own Geiger avalanche diode, which is used to convert the input signal into an electric impulse. Now, these electric impulses are based on the intensity of the incoming signal. Say the incoming signal has a data rate set to 1, then the Geiger diode will be set into an avalanche breakdown, and using this breakdown and distortion technique, we can create a digital like signal on the receiver side. The only downside to this is that the time between the breakdown and returning back to its original state, which is called hold off, is of about 1 microseconds, and during that, if any signal is hit on this particular diode, then it will either create an unnecessary high state or go back to the breakdown, miss the signal. So either of those cases are not to or use and will create an error in the input signal. For that, many techniques can be used to overcome that particular difficulty. One of reduce the intensity of the input signal, and we can do this by spreading the signal over an array of receptors, as we are planning to do within this project. So this will overcome that particular disadvantage of the Geiger diode. Also, some other caveats of using this GAPD, which is the Geiger diode, would be the dark counts, which are the high states generated by the thermal disturbances caused within the particular diode, and which would create a false breakdown. So we can overcome that easily by uh, creating controlled environment situations, as like active cooling the particular array, or we can also shield the telescopic arrangement from any direct sunlight or any other light sources. One other particular we can say disadvantage of using an GMAPD would be uh, the generation of the Geiger mode avalanche photodiode GAPD, created by the MIT's Lincoln Laboratory, has an efficiency of over 45%, which is termed as photon detecting efficiency. So every 100 photons, about 45 of those would be detected by the Geiger diode. Now this may seem a very low count, but in comparison to other diodes, it is very high, and especially in terms of photodiode. So MIT's Lincoln Laboratory has done great work to build this particular device, I would say, and a lot of work has been put into creating it to be very stable in terms of thermal conditions, and also in the states when it is not actually receiving the signal, so we can decrease the number of dark counts that we have. This particular GAPD would have less than 50 kilohertz of dark count rate per communication signal. So that is a very notable achievement. One way they have been able to do this is by the design of it. So it has a very novel approach in designing the photodiode, within which it has a particular cover layer below which the substrate of the detecting photodiode is situated. The photodiode itself is made of indium and phosphate, which they call the INP substrate. But over it we have an covering layer of iron gas, which is indium, gallium arsenic, and phosphorus, which acts as an absorber for any environmental disturbances or dark counts that might affect our incoming signal. Also, we have the passive polyimide layer, which will completely block out any environmental any environmental incoming noise signals. Also, the way the input signal is captured is very unique. They create a sort of a ridge within which there is a bump, and only through that small aperture will the input signal be allowed to enter. So this will give us great benefit in terms of we'll have control over the intensity of the input signal, and so we can very easily eliminate any uh, extra noise or other disturbances that may have been added and may have, say, very high frequency, so that or a certain parameter like amplitude that can be filtered. uh, so that is the end of the second part. We'll now look at some of the techniques that we can uh, say would make the cost of the whole mission more uh, reasonable, and as it is creating an array of receptors is an substantial effort and would require a lot of money, time, engineering and resources. So one way to do this, and also a lot of research has been done in terms of placement and how the array actually should be designed, and they have tried many different modes of placement of the array, also trying out the equatorial plane, say two telescopic arrangements are kept on side to side, or they also tried the elevation design, so one on top, one on below. And from those experiments, the best outcome has been seen to be used seen to be achieved by using 2 to 4 the particular optical telescopic arrangements, and you can place it in top below manner to achieve the best signals, to achieve the best efficiency. This particular arrangement can be very easily made with the use of minimum resources, and it is very cost effective compared to a say single aperture big telescope. Now, while we are talking about multiple receptors, one might be tempted to say that why not just create a whole, uh, like a solar array, a whole bed of receptors and lay it out. But actually, the cost of the multiple receptors is not linearly connected to the area of coverage. So we don't always want very small receptors spread out over a big area. Actually, we want medium size receptors receiving the input signals and processing them. For this mission, the best scenario has been calculated to be using 4 meter class telescopes, which are in a top to bottom conditions, and at a time we can connect 4 of those. So that marks the end of our review. I know I missed many of the technical details, but I think that this gives a very brief overview of the different advantages of using multiple array receptors. And I hope that great work is done in this field. I myself would like to explore more about optical communications, and I do see a great advantage of using it in terms of interplanetary or even intergalactic communication systems. One thing that that struck me while exploring this paper was that even though we might be benefited by using it within near range, relatively near range, while we go for deep space, very deep, say intergalactic or even beyond the boundaries of the galaxy, uh, there might be some troubles in connecting with that particular body, as there is not always an straight empty path between a particular spacecraft and Earth, and as it is the time delay between the communication signals is a uh, long time period between object which is far away. Even though it is moving at the speed of light, it will take some time. So for missions which go beyond our galaxy or even beyond our solar system, we'll have to further optimize this technology. One such way that I thought would be possible is to create an onboard telemetry and tracking system. Instead of sending signals from Earth, we'll send signals from the spacecraft to uh, monitor it and keep it in position for the receptor and the transmitter to remain in sync. So yeah, I think that's all I have to say about this paper. I hope that you learned something new, and see you soon.